Alright, hello everyone. It's April 19th. Alright, on a trip, have a meeting tomorrow. So let's see. And also I don't bring my pad with me, so go back to the old way of just explaining through words. Alright, maximum width of a binary tree. Given the root, return the maximum width. What's the width? Among all levels. The width of one level is defined as the length between the end nodes, the leftmost and the rightmost known nodes, where the known nodes between the end nodes that would be present in a complete binary tree extending down to the level are also counted into the length. So this one is 4. That's what it means, right? The known nodes is this one, right? Between the end nodes that would be present in a complete would also count. So in this case, that's 4, right? So 5, 3, no, 9. This is not 8 because they're talking about a complete binary tree, right? So complete binary tree doesn't have to fill the last one. Is it a binary tree, right? It starts with a binary tree, so it's always going to be the last, right? What about this? This should be, that should be 2. I see. So, first in my head is BFS. But we will encounter some issue with BFS because we do not pass. Now, basically, we need to pass null, but null is hard to pass. Like we can pass null here, then we know this, but the next one it's hard to know. So that's probably not the way. What might be the way is index. Index. You thought about index? Like every level, we can give index. If it's 0, right, 1 and 2, and this one will be 3, right? I can actually write it out. We have 0 at the top, 1 and 2, and this is 2 times 1 plus 1 will be 3. We don't have this, but we have this. This one is 2 times 2, right? 0, 1, 2. 2 times 2 plus 2. 2 times 2 so that'd be 6, right? So this will be 6. I mean, maybe we should start with 1, which is easier. It's just times 2 and then 2 times 1. Yeah, let's start with 1. Nah, it doesn't matter. It's the same thing. Okay, so from here, I go to the left. It was 2 times 3 plus 1 would be 7. Right, and then we go this one. This will be 2 times 6 plus 1. 2 times 6 plus 1 is 13. So this is 6 minus 3 plus 1. So this level is 4. This is 13 minus 7 plus 1. So this level is 7. Yep, I think that's it. This is the same thing. We have 0, 1, 2, and 3. So the largest width is this level, 2 minus 1 plus 1, which is 2. Okay, so we can solve this. Oh, I have to make it bigger. Okay, so shall not be too hard. So it's BFS with indices. Okay, BFS with indices. So how do we? So we just need to know indices, right? Then we'll say the Q, right? Q will equal to your root and your index. Okay. Say, well, Q temp for node index in Q, right? And then rest equal to 1. Hold on. Number of nodes, yeah, so at least the width is 1. And then we're gonna say why don't we handle it? We can handle it at the end, or we can handle it at the front. We might as well handle it at the end. So we say if node.left, right, then temp.append node.left and 2 times index plus 1. If node.right, temp.append node.right 2 times index plus 2. Blah blah blah. Q equals temp, and the rest are equal to maximum rest temp, not temp, Q minus 1 1 minus Q minus 1, no, 0 1 minus, no, plus 1. And we'll keep going until we are if Q, right? If Q. And then we'll return res. That shall do. Okay, let's give this a shot. See if it works. Looks good. I want to try another test case with a single one. Okay, let's give it a shot. Ooh. Oh, I got it. I just saw I have error previously. So what type of method did I use previously? So that's February last year. And this is July, almost 3 years ago. Okay, so we can take a look. This is the Yep, that's exactly what I did. The same. Actually, this is better because we put this one up and higher. All right. This was 2 years and 9 months ago. Current level. Same idea. Okay, so this one's done. $662. Put index right on each node, and then BFS. Shall be it. I don't know, every time I try to copy and paste, it's not working every single time. Okay, so that's that. Now we have to go back to this, and we have our issue. Hold on. This is what we have yesterday. And we have this. Oh, we already have it. Yep, that's the problem. Okay, I'm gonna draw it. So what was the issue? So we have 4 1 1 1 1 3 1 1 1 1 2 1. Oh, 1 1 1 1. I see. Okay, so it passes all the 2 checks, and then I was trying to. Okay, so we can say a something something something, right? Because this position is a 1, which means 0, and then with this only 1. So I'll say the second one has to be A, right? Second one has to be A. And then yeah, it doesn't match. It does not match. Does not match. So what was the idea initially? So the idea is we have a candidate, right? So we will go from J. J, the first one is 1, right? So we check I is 0, so we check 0 1, right? So 0 1 is is this, right? We say if it's equal to, now it's not, it's equal to 1, right? So we say candidate will equal to result I. So that's why I have 2 A's, right? And then so far so good, right? And now I'm looking at J. J is done, right? Now I is done. Next one, J is equal to 2. Okay, J is equal to 2. So we are looking at 0, 2, and 1, 2, right? So 0, 2, and a 1, 2. 0, 2, and a 1, 1, 2. So we're looking at these two. So what's 0, 2? 0, 2 is going to be 0, 1, 2, 3. 0, 2, and then 2, 3. Okay? And 1, 2 is going to be 1, 2, 3 with 2, 3. Basically, we're checking the position, the 2 with 0 and 1 to see which one works. But as you check, so in here, they're both 1, right? So 0, 2, and then 1, 2. So 1, 2 is 1. That means 0, 2 is 1. That means 0 is equal to 2. Right? 0 position is equal to 2. Okay, hold on. The first one, right? The first condition, 0, 1, 2, 3. Compare 1 to 3. So we have 0 is equal to 1. 1 is not equal to 2. And 2 is not equal to 3. Right? And now we have 0, 1, 2, 3 compared to 2, 3. Now we have 0 is equal to 2. And 1 is not equal to 3. 0 is equal to 1. And 1 is not equal to 2. Therefore, 0 shall not equal to 2. But now I say 0 is equal to 2. That's why it doesn't work. What do you think? How can we detect this union find? Union find. That, my friend, is not too bad an idea. Union find. Think about it. What would union find do? Union find, right? If we have the initial comparison, right? Yeah, but everything we just do the initial comparison. We just do the initial comparison. Like we say 0, 1, right? Each cell tells you the initial comparison. Right, we have 0, 1. If LCP 0, 1 is equal to 0, that means 0 and 1 are not the same. Right? So we do not union them. Which means if they can be unioned together, that's already a bad thing. Right? Wait, is that because initially everybody's not unioned together, right? So at the beginning, if they're not unioned together, that's good. If they are, and they originally is not unioned together, then we union them? I mean, we can, right? If they're the same, then we should union them. So we can go through the first, like that. Let's think about go through the first row. 0, 1, 0, 2, 0, 3, 0, 4, right? 0, 1 could determine whether 0 and 1 are union together. 0, 2 is whether 0 and 2. Actually, it's more complicated than that. 0, 1 I did. 0, 2. Hold on, think again. We are thinking 0, 1. then we know how many are supposed to be the same. So we can union all of these, right? So 0, 1, 2, 3, like all of these, we can union them together. And then we see 0, 2, right? When we see 0, 2, because 0, 1, we handle the sum. Hold on, 0, everyone, at least we can handle 1. So 0, 1, 0, 1, Zero, 1 handles a lot. So we know the length of, so we know how many are the same, right? How many are the same? So we can say 0, 1, 1 and 2, 2 and 3, like how many of these are the same? So we can put them together. Union them, okay? And then we can do 0, 2. So for 0, 2, hold on. So if we do 0, 1, we have 0, 1, 2, 3, and a 1, 2, 3, right? So now we know how many are supposed to be the same. Okay. Okay, so we know how many are supposed to be the same. So these will all be unioned together. How about we take a look at 1, 2. Because I just handled them, right? Oh yeah, it should be smaller. Oh, I didn't use that. Hold on, I forgot to use the other property, which is diagonal wise it always decrease, right? Diagonal wise it always decrease, because the previous is always going to be this, right? Diagonal wise is always decrease, and this point is 0, 1, 2, 0, 1, 2, 3 compared to 2, 2, 3, right? And then its diagonal coming down is going to be 1, 2, 3 compared to 3. Yeah, so it has to. Okay, so that's another thing we can consider, which actually means, it does mean that the first row shall give you all the information, because the remaining is, well, not necessarily, unless it's a 0. If it's a 0, then you don't know, right? If it's a 0, you don't know. Okay, if it's not a 0, right? If it's not a 0, then the remaining is, basically it's just all good. What if it's a 0? That means, that just means the first one is not the same, right? Then you cannot predict. Then you have to go look down the, yeah. So which means I will look at position 0, 1, okay? I look at position 0, 1. If 0, 1 has a value, then we can trace it down, right? We can trace it down to the next one. So what if the 0, 1 has a 1, right? What if 0, 1 has a 1? So just first one's equal. Then 1, 2 shall be 0. Okay? How about 2, 3? Then 2, 3 we don't know. 2, 3 we have to check. We have to check 2, 3. We have to check 2, 3. Okay. Yeah, we have to check 2, 3 because 2, 3 is not the same. 2, 3 is not the same, right? So the previous is the same, and 2, 3, then this thing is not the same. Then we can, always set. Now, when it's not the same, we cannot set anything. Yeah, the first, so we have the previous is all fit, and the first one that does not fit, right? The first one that does not fit. If it's the first one that does not fit, we should always be able to set it to B. It's okay, right? We can always set it to B. Okay, let's say we set it to B, the first one that does not fit. Then what? Then it will continue, right? Then it will continue. Or either we end. Then we go to the next one. If it fits again, then we just continue. If it doesn't fit, what if it doesn't fit? What if it's 0 followed by 0 followed by 0? But we are pushing from front to the end, right? So if it doesn't fit, we'll always do something that's different. So we always can go back to A. What are you saying? 1, 1 position. A 0, 0, 1 position. 0, 1 position can tell you how many A's there are. Additional A's there are. Right? And of course, we also have this check. So this is also going to work. So now I can tell you how many A's there are. So we can say, okay, I set up these A's, and then we'll just go down, and they need to decrease. Okay, so we go diagonal down. Right, we go diagonal down. We're gonna go in the A, and if it's different, we're gonna go A. If the next one becomes 0, then we just put a B. And next one, if it's 1, then we put a B again. If it's not the same, then we put an A. So that can how we form. And then we have the thing, and then we need to check what? Check the remaining. Right? How do we check the remaining? Now we form everything. Now we just say if this and this, if they match, right? If they match, right? 0, 1, 2. So we should say 0, 1, 2, 3, 2, 3. So we actually can compare 0 and 2, right? 0, 1, 0, and 2, and see if these are the same, right? Hold on. So what you're saying is we can set it to, we don't need to do this, we can do this, that's fine. Okay, diagonal, symmetric, and then we're gonna go diagonal down. Okay. For J is 1 to N. That's correct. Then for I in range, so actually no. We go diagonal. So this J, and then for I in range 0 towards n minus j. Okay, right? N minus j. N minus j. So if j is 1, so n minus 1. So n minus 2. So I will end here. Okay, and then we'll do, so this one's not j. Let's put it as k. So what is j? J shall equal to I range. So every I plus so I is 0, j is 1. No, yeah, j is 1. I is 1, j is 2. So k plus I plus k. Right? J is I plus k. Because if k becomes 2, right? So it'll be 0, 2, and 1, 3. Yes. Yes. Okay, so now I have item j. And we can say if LCP, right, ij is larger than 0, right? If it's larger than 0, then what we need to consider is two things. First, if I is larger or equal to 0, well, actually, we should gonna go, yeah, I will always be larger than 0. So if I is larger than 0, right? If I is larger than 0 and LCP, diagonal, I larger than 0 and j larger than 0, and this I minus 1, j minus 1 is not equal to LCP ij plus 1, return this, right? That's the case. Diagonal wise, if the current one, actually if the current one is larger than 0, right, that means my diagonal must also be larger than 0, and it has to be one more than me. That's actually not true. That's actually not true. Because the previous one can be 0. So the previous one has to be either 0 or, Lord. If the previous one is, and this is and, right, it's not equal to 0 because the previous one can be 0 and this is not equal to, that's when it's bad. Okay, otherwise you might as well just say, actually this, you might as well just say if I what are you trying to say? Let's find a case that's possible. What's possible is, this is the first one, right? This is the first one. So if I is equal to 0, or LCP I minus 1 and j minus 1, right? Or this is equal to LCP ij plus 1, or LCP I minus 1, j minus 1 is equal to 0. These are the cases that's good, right? I equal to 0 means it's the first row, so it's always good. And if I is not equal to 0, then it's not the first row, but it's fine. Then we check the diagonal, it has to be the current plus 1, right? I mean, that's good. Or the diagonal can be 0. That's also fine. So in fact, this case and this case is exactly the same, right? It's exactly the same, but I don't want to redo the LCP, so we have to check it 2 times. So when that happens, we say res, right? And then we're looking at J, right? We're looking at J. When, let's say, if res J is equal to this, which means we have not fitted yet, then res J shall equal to res what? I, right? Because ij is larger than 0. That's why we can check. If it's not equal to, means we set a value already. If this is not equal to res I, then we will return this, right? Or here, we also return this. Can we combine them? Which is only this, right? Yeah. So what we can do is, if well, also is the case if they're the same, right? If they're the same, then we're good. We just ignore. Okay, let's do this. So that's else. Else is, it's a 0, right? So the current is 0. If the current is 0, which means these two do not match, right? And if they do not match, then we can say if res J is equal to empty, which means we haven't done it, then we can say res J shall equal to A if res I is equal to B, right? Else B. Right, if res I is equal to B, then res J can be A. Otherwise, if this is other than B, then it should be B. If res J is equal to res I, that's also a bad thing, right? That's also a bad thing. Because they cannot be the same. They have to be different. Right, they have to be different. So this is what we do diagonal down, and then eventually we'll return this. Does this work? Oof, list out of index. Which one? First one. Yep. Hold up. K. What is K? K is 1, 2, or 3. Okay, so K is 1. So I will 2. So I will never go out of bounds. I know I will not go out of bound. The problem is J, right? So wait, hold on. N minus J? That is not correct. It's N minus K. str. Oh yeah, it's don't have to. Oh, I can just join them. Ooh, look at that. I mean, symmetric. Yeah, we still need to check symmetric, but we don't have to check this, I think. because this is checked. Wait, do we need to check this? What if it's too big? Okay, well, let's say, well, this will already set it up. Right, it has to be this in order to be considered. If it's not, so I think we just need to check for symmetric. That should be fine. No, it's not fine. Oh yeah, the first row, we did not check the first row. Oof. Check symmetric, right? And there's an and the max possible value for each cell. Okay, and then this we will examine. Let's say examine LCP diagonally, right, from top left to bottom right. Right, for each LCP ij, right, if it is larger than 0, right, then it must be one smaller than LCP I minus 1, j minus 1, unless I is equal to 0, right? Must be one smaller than or LCP I minus 1, j minus 1 must equal to 0, right? Also, when LCP I and j is larger than 0, we must have res I is equal to res j. So this is another place, right? This is another place where check can be made. I'm not even sure this is right. You should write so much. Yeah, I want to do this somewhere else. Right? This is basically this situation. Okay. So here, this situation's if LCP ij is equal to 0, right? If it's equal to 0, that means res I is not equal to res j. Right. This is where we can check for accuracy. And also, since we are producing res from left to right, any mismatch will be a mismatching. It will be B if the mismatch is A, right? Or A if the mismatch is B. I don't know, you wrote so much, it could be wrong. You thought about that. It could be wrong. I know, it could be wrong. Alright, these are work. Yeah, I know, it's gonna try and error. Try it again. Oh, that is still not right. Output. Yep, we have a C. We have a C. Knew it. Knew it. Man. This is tough. Yeah, if you do, yeah, I can see like if you do, so this, right? This is giving me issue. We should not set it to. So what should I set it to? What should I set it to? Maybe we need to recursion this thing. Yep, we have all the zeros. We have all the zeros and we cannot make a decision. I mean, we have A and B, that's fine. But the next one is hard to say, right? The next one, I just took it as A. I go back to A. Yeah, this line is wrong. This line is wrong because it could be many different options. It could be many different options. Maybe this part needs to be I don't know. To be what? Like recursion, right? For each position, we can try B, C, D. We can just keep trying, and then until the first one that matches. And if we try everything and it fails, then that's gonna be a fail. All right, I'll stop right here. Yeah, this needs some more thinking. Okay, I'll deal this tomorrow. Tomorrow, yeah, I'll be home, but I'll be home at very odd times. But I'll think about this. Yeah, this basically this line. Right? This line is trouble. We have to try these one by one. All right. Anyway, I will end it right here and see you guys tomorrow. Adios.